All right, guys, if you're back for more, I can only assume that either you love statistics as much as me, or you feel like one more example would help you really understand z-tests. I'm going to go with the former. Okay, so when I was little, I noticed a couple of things. First, that I had a different last name than a lot of the people around me. Now, everybody's got a different last name, but mine was hyphenated. One of those names in particular, Foos, was relatively unusual as far as I knew. I mean, I knew plenty of family members with the last name Foos, but when I was growing up in Miami, I didn't know anybody down there named Foos. I'd never heard of anybody on the news named Foos. I've heard of Clarks, right? And so I remember asking my dad where the Foos name came from, and he said it was German. And the German word for foot is Fuß, right? F-U-S, the little bee-looking thingy. And I said, okay, well, that doesn't really answer. I mean, we're named feet. We're named foot for some reason. He said, well, there's this old expression, fleet of foot, means fast. And said, I think it's because we come from a very fast family, that we have these particular genetics that lead to us being fast. As a young kid, I thought, well, I guess I'm pretty quick when we play. When I play with my friends, I'm pretty fast. And my dad said the same of him when he played baseball with his friends as a kid. He was always one of the fast ones. So I thought, well, let's put this to a test. All right, let's see if there's any evidence to support the claim that my family, being named Foos, are faster runners, let's say, than the national average, right? The population. Now, the only way I could figure out the national average on running the mile was literally just to Google the national average and running the mile. So don't hold me to this actually being an authentic national average. We're just going to treat it like one for the purposes of this example. So what I found, that it was the national average would be 10 minutes and 13 seconds. This comes with a standard deviation of 76 seconds. So we know the population average and the population standard deviation. Those are prerequisites for a z-test. So we have them, good, we can run a z-test. So the question now is my family running speed different from that national average? So I get 6 individuals in my family and I have them all run the mile and I time them. Right, so my dad runs it at 13 minutes and 48 seconds, and his younger sister runs it at 10 minutes and 10 seconds, and his younger brother runs it at 7 minutes and 54 seconds. He is one fast dude sometimes. Aaliyah, his daughter, runs it at 9 minutes and 22 seconds. I ran it at 8 minutes and 38 seconds, and my cousin David ran it at 9 minutes and 48 seconds. So now you know a lot of my weird family's names. So how do we go about this particular calculation? We know population average. We know population standard deviation. We know sample size. What else do we need? Do you remember that z-statistic formula? Well, what we need in this case is sample average. We know sample size of 6, right? There's 6 people that ran the mile there. So we can get a sample average pretty easily. Let's convert this all to seconds, first of all, because you can't create an average of it while it's in minutes and seconds. So convert that all over into a new column, and then let's find the average of that. Okay, the total is 3,580 divided by a sample size of 6. So our average running time for the individuals in my family is 596 seconds, 0.67. Okay, now we need to do the same thing with the population to convert that to seconds as well. So do that and go ahead and put all of our given information from the problem up at the top. The population average is 613 seconds. The population standard deviation is 76 seconds. The sample average of Foos family members comes in at 596.67. So there's already not a whole lot of support for us being faster than the population. The question now might be, are we different enough that we are in fact slower than the population? So sample size of 6. Step 1 of hypothesis testing: populations, distributions, and assumptions. Populations first. All individuals with a last name Foos versus all healthy adults. Right? Those are our 2 hypothetical populations. Not just the Foos family members that I found, but all the individuals who have that last name who theoretically would have that Foos legend of quickness, right? Versus all healthy adults who don't have that last name and what their running speed would be. Comparing a sample mean to a population mean, that means our distribution is going to be a distribution of means. All the possible values that a sample mean could take on, ours took on this value. Is that different enough that we would say it's a statistically significant difference? Our test, again, the only one we know so far, but because we know population mean and population standard deviation, that clues us in that we can use a z-test. Okay, that's really the only way you can run a z-test is if you know that information. It's kind of an ideal world. It says you know so much about the population that you can really accurately, with just a sample size and sample average, determine where it lies within that larger population. The data are interval, right? These are running times. They are definitely the definition of interval. It's not random selection, but that's okay. We're not trying to generalize to the whole population. We're trying to generalize to Fooses, and it's just kind of a joke example, so we can break this assumption a little bit and not worry too much. I also told you we are going to regularly break the third assumption. Still not a huge deal. We're doing it just for the purposes of calculation, so that we do the math on only 6 numbers instead of on 30 numbers. Okay, so again, we're going to sort of fudge that last assumption for most of the examples that we go through in class. Step 2, we need to state the null and research hypotheses. Well, the research hypothesis was that people with a last name Foos do run at different speeds. It's originally going to be faster, but let's call it a non-directional hypothesis and say they could run faster or slower than the national average, but we run different from the national average. That means the null hypothesis then is that people with the last name Foos do not run at different speeds than the national average. And what we're going to do is see if we can find any support for the null hypothesis. If we find any at all, then we're going to say the null hypothesis is probably the case, and we're going to reject the research hypothesis. Determine the characteristics of the comparison distribution. Remember, I told you this is just basically calculating standard error. You're finding out how variable, how spread that distribution of sample means is, so that we can figure out where our sample mean lies within it. So the population mean we know to be 613 seconds, 613.5 actually. So that population mean carries over to the mean of this comparison distribution. The standard deviation of 76 seconds, the sample average of 596.67, and a sample size of 6. We know all that information already. To get standard error, we need to take standard deviation and divide by the square root of sample size, right? Sigma divided by the square root of n. Plug those values in then. 76 divided by the square root of 6 gives you then a standard error of 31.02. Okay, so then we move on to the next step, and I'm going to replace standard deviation with standard error, right? This 31.02. Determine our critical values, our cutoffs. In behavioral sciences, we use p equals 0.05. I'm going to continually remind you of that because in other fields, they don't always use p equals 0.05, which means that we're willing to take a 5% risk that when we reject our null hypothesis, we're wrong, right? It's a type 1 error. The risk of type 1 error, that is 5%. Essentially saying that in 5% of the cases or less, this difference would occur if only chance were operating. If chance is not the only thing operating, and instead the Foos family runs different, then that would be a really unlikely event to occur, right, due to chance, unless maybe it really is that the Foos family runs different. We're going to go right now with the non-directional hypothesis, but as you see, we'll talk about directional hypotheses and how to do those as well. It really just means that the 5% we're looking for in our cutoff value is in both tails instead of just in one particular tail. Again, I'll elaborate more on how to do directional hypothesis testing in subsequent examples. So this z table is going to list the percentage between the mean and that z score, that z statistic we need for our cutoff value. We know that we're working right now with a two-tailed test, which means 5% in each tail, which means 2.5% from each, 2.5% in each tail. We've already done this in the previous example. We know this cutoff, the one that corresponds to the 47.5% between mean and z, leaving the 2.5 out there. That's a plus minus value of 1.96. Now, before we move on, let me show you how you do this for a one-tailed test. So let's say we were simply predicting that the Foos family was faster than or slower than, not that they were different from. In this case, we would need a z statistic that's on just one side of the distribution and keeps all 5% in that tail. So instead of looking up the z statistic that has 2.5% in each tail, we look up the z statistic that would leave 5% in a tail. In that case, 45% between the mean and z, that corresponds to a z critical, a z cutoff of 1.65. So if we were predicting sample mean being greater than the population mean, so Foos family running slower because a greater mean, a greater run time would be slower. Well, the z statistic is sample mean minus population mean, so we'd be predicting a large number minus a small number in that case, and we would want to then use a positive z statistic because we were expecting then for it to fall on that side of the distribution. If we were instead predicting that the average running time of Fooses would be faster, and thus a smaller number than the population average, then that prediction would predict sample mean minus population mean to produce a negative number. And so we'd want our z statistic to be on the negative side of the distribution to see if we fall far enough into that tail. So again, we'll go through that a few more times with other examples, but a sort of introduction to how we might do it if it were a one-tailed test. Okay, so we're really here at the end. Does a foos live up to a foos? Calculate the test statistic. We know all of our values that we need to plug in here. So put in the sample mean, population means, standard error. Subtract out, get our z statistic. We get a negative 0.526. Our cutoff value was a 1.96 plus or minus. So our z of negative 0.53 doesn't quite make it there, right? It's not into the tail. Remember, keep drawing these things. Draw them, draw them, draw them until you feel like you really don't have to anymore, because it'll help you always make the right decision. Speaking of which, what is the decision? Well, in this case, we are no different from the population mean, right? We fall well within that predictable, likely range of variability that would occur due to chance. So mathematically, we'd say, right, the z of negative 0.53 was less than the positive 1.96. However you want to sort of word that mathematically. We fail to reject the null hypothesis. More importantly, I always want you to be making decisions in words, right? So saying something like the average 1 mile running time of foos family members is not different from the national average running time. Now, American Psychological Association dictates how we report our statistics. We are psychologists. This is APA style. And so at the end of a sentence like this is where you report the results of your hypothesis test, right? You've probably seen this in results sections before. So for a z-test, at the end of your sentence, you put a comma, you put the lowercase italicized z, and then in parentheses, you put your sample size, so the n of 6 here, we place that in there, equal to whatever your z statistic was. Now, typically we report those as the absolute value, so we wouldn't report the negative value, but I put it in here anyway, negative 0.53, because the probability of this occurring due to chance alone is greater than 5. Right? It's definitely not less than 5. It's not an unlikely event. It's a likely event. We then write lowercase italicized p greater than 0.05. Right? And then you might say something like the legends aren't true, right? However you want to word your conclusions. But that's it, right? That's another example of a z-test. So hopefully you feel a little bit more comfortable with that. If not, go try the homework, try some more examples, watch the video again, see if you can follow through those steps. And if all of that doesn't work, then get in touch with me and go to SI and watch some more videos of stuff online if that helps you. Just make sure you know how to do this stuff, because it's really not all that difficult once you sort of get it to click. All right, cheers.